Since we know there are two types of measures of dispersion, absolute measures of dispersion and relative measures of dispersion. In this module, we'll be talking about few absolute measures of dispersion. Absolute measures of dispersion are of different types. That could be range, quartile deviation, mean deviation, that's also called mean absolute deviation, and standard deviation. And it has another variation in it that's called variance. Let's talk about the first measure of dispersion, which is range, which is defined as the difference between the maximum and the minimum value in the data. Range are very sensitive to only the most extreme values in the list. Range of a list is 0 if and only if all the data points are at the same point. They're all equal. Range is generally denoted by the difference of xm minus x0, which is xm denotes maximum value and x0 denote minimum value. Over here in this bar graph, we can see that our data has spread out from the 4 to 16. So this whole red line marks the overall range of our data. Let's take an example where we measured these GRF measurements from the 20 dogs. Here in this data, our minimum value is 14.6 and the maximum value is 44.0. And if we want to calculate the range, we'll just take the difference of maximum and minimum, which is 29.4 newtons. From here we can see that our overall data ranges from 14.6 to 44.0. There are a few pros and cons that comes with the range. It's best for symmetric data with no outliers, because other measures, the range also get affected by the outlying observations. It's easy to compute and understand and good option for ordinal data. Whereas it has its disadvantages that it does not use all the data. It only uses the extreme values in the data. That could be lower extreme or an upper extreme. Moreover, it is very much affected if there are extremes and these extreme observations are outlying observations. And range only shows maximum spread. It does not show any shape of the distribution, which is one other task that we can perform using different measures of dispersion. Absolute measures of dispersion have another type that's called quartile deviation. Quartile deviation is heavily dependent upon the quartiles, which are the cut points. Quartile deviation is the half distance between the upper quartile and the lower quartile. Upper quartile is the 75th percentile or third quartile, and lower quartile is the 25th percentile, which is the first quartile. These quartile deviation, it essentially describes that how much the middle 50% of the data varies, also known as semi-interquartile range. If we look at the formula of quartile deviation, we can notice that quartile deviation is equals to interquartile range divided by 2. Since we are dividing it by 2, that's why we call it semi-interquartile range. And we call it interquartile range in the numerator because it's the difference of third quartile and the first quartile. And we use usual method to calculate these quartiles as we discussed in the previous modules. If we look at this frequency curve, we can see that this point represents the first quartile and this point represents the third quartile. Quartile deviation talks about this 50% of the data and it completely ignores the rest of the 50% of the data. The method to determine the interquartile range is that we firstly arrange the data into ascending order. Over here, we are actually trying to calculate the interquartile range because this is more commonly used as compared to quartile deviation. In the first step, we arrange the data into an ascending order. In the second step, we find the position of the lower quartile and upper quartile using the following formulas Q1 and Q3, which are very much familiar to us. Then in the step 3, we identify the value of the first and third quartile using the mechanism that we already have talked about. And in the step 4, we calculate interquartile range using the following formula, which is just the difference of third quartile and first quartile. If we look at the same example we talked earlier, from the histogram, we can clearly see that there is one outlying observation, but we have Q1 right there, Q3 right there. And Q1 and Q3 are actually not getting affected by this outlying observation. Whereas the median is 30 point something. And it goes on for the other values. We use the usual method of Q3 and Q1. Hence, using this method, interquartile range turned out to be 6.275 newtons. And it can be represented on this histogram that it is 6.27, which is containing almost middle 50% of the data, and it excludes this 25% on the below side and this 25% on the upper side of our curve histograms. So there are a few properties of using the interquartile range. The interquartile range is generally used in conjunction with the median. Together they are useful to characterizing the central location and the spread of our frequency distribution. These are mostly recommended if our data is skewed. For a more complete characterization of a frequency distribution, we use 5 different values, which is the minimum observation, the maximum observation, it's the median, first quartile, and a third quartile. Together, these 5 observations give us a very good description of the center of the data, of the spread of the data, and the shape of the distribution. There are a few pros and cons of the quartile deviation as well. The quartile deviation is good for ordinal data. It's good for skewed data. It ignores extreme values, as we discussed earlier in the case of histogram. It's more stable than the range because it ignores outliers. There are a few demerits of it. That includes it's harder to calculate, as the calculations of quartiles is laborious. It does not use all the information because it ignores the middle 50% of the data. As we see, the tails are almost ignored in both the cases. Each absolute measure of dispersion can be converted into its relative measure of dispersion. And relative measures of dispersion are used to make comparison between different data sets, irrespective of their units of measurement. Thank you.